This is Module 5, Lecture Notes 9. Last week when we left off, I had just introduced to you how to balance simple types of reactions. And this week we're going to build on that. We're going to learn about some different types of reactions, how to write them, and then we will continue our balancing skills by balancing them. Reactions are all around us. They happen in the air we breathe, in the gas we put in our cars, in the combustion of the engine of the car. When we cook our food, there are reactions happening in our everyday lives all around us. So let's take a look at some of those different types of reactions. The first one we're going to look at is called a decomposition reaction. And I always remember that when something decomposes, it breaks apart. Think about your trash decomposing. It's breaking down. So basically, you're taking your first compound and you're breaking it apart. So in this first one, if we have water, to break down water into its individual elements, we would separate the hydrogen and the oxygen. Now, one thing we did talk about last week was that there are a couple elements that can never be alone. Do you remember if hydrogen and oxygen were some of those? Let's take a look. If one of your elements is in the special 7, remember our 7-up rule, it cannot be by itself. It has to be written as a diatomic. It needs a partner. So this is how you would break apart water. We would say water decomposes into hydrogen and oxygen, and those are both gases. And since we know how to balance reactions, let's do that. I have 2 hydrogens on the left, and I have 2 hydrogens on the right. That seems good. But over here I have 1 oxygen, and then I have 2. So the only way to balance that is to put a coefficient of 2 out in front of your water. Well that made 4 hydrogens, 2 times 2, so I also need to make 2 times 2, 4 hydrogens. So this one would balance 2, 2, 2, 1. Okay, and if you want to write yourself a note for what we did, I would just write separate each element. You can also write watch your diatomics. Okay, let's try another one together. I've said that I want you to decompose ethanol. So ethanol is C2H6O, and we want to break that down. Remember, decomposition is breaking apart into individual elements. So we have carbon and hydrogen and oxygen. I wrote 2's after the hydrogen and oxygen because they follow the diatomic rule. Carbon is not part of that group, so it's okay by itself. I want you to take a second and practice balancing that. You might see that you have 2 oxygens on the right, so we could put 2 oxygens on the left, 2O. Now that tells us how many carbons we need, and 2 times 6, this should be 6 times 2 for the hydrogens. 2, 4, 6, 1. Remember, when you're balancing, you can start anywhere. You're going back and forth until you get the reactants and the products to be equal. Okay, this last one I would like you to pause, and I want you to try writing the whole thing out on your own. See if you can do it before listening to my answer. All right, so here's what I have. I have our compound, SiH3F, and I'm going to decompose it, which means I make each element separate. The reason hydrogen and fluorine have 2's after them is because they are part of the diatomics. Now you can go back and put coefficients in front to balance. Often when you have 3 of something and 2 of something, the only way to get those equal is to make them both equal to 6. Okay, so I have 6 hydrogens on both sides. Now I can do the silicons, 2 silicons, and the fluorines, 2F, F2. So I'm good there. So that's how you do decomposition. Remember to start with your compound and break it apart. Watch those diatomics. All right, let's move on to the next section. We're going to do the opposite of decomposition. So these are called formation. If you're not breaking something down, you are forming it. Or sometimes you'll see these called combination. You're combining them. 2 or more things combine to form a single compound. So it says in this one, we want to show the formation of magnesium carbonate, MgCO3. So we know that we are making MgCO3. And we're going to make that by using the individual elements, magnesium, carbon, and oxygen. And they're going to combine together to form magnesium carbonate. So I take magnesium plus, how do I write oxygen? Oh, carbon's next, sorry. Carbon. And how do I write oxygen? O. It's always O2. It cannot be by itself. Okay? Once you have all of your things written out to form your compound, then you think about balancing. Here we have another case where I have 2 of one element, and on the other side of my reaction I have 3. So let's do this. And then you can go back and figure out what magnesium and carbon need to be. 2 magnesiums on the product side, 2 magnesiums on the reactant side. Same thing for carbon. And that's how we would balance it. 2, 2, 3. 2, 2, 3, 2. All right, the last type of reaction you need to know for this class is called a combustion reaction. And I think combustion reactions are really important because anytime you burn a carbon compound, it is a combustion reaction. So if you light your grill to make some cheeseburgers and you're lighting your propane, that's the combustion of propane. If you light a lighter to light the birthday candles on a friend's cake, that is the combustion of butane in the lighter. So these type of reactions you actually see quite a bit in your everyday life. So I want you to show the combustion of butane, and I gave you the formula here. So butane is C4H10. Now, combustion reactions can be tricky and simple all at the same time. The reason that they're simple is they are always a carbon compound burned with oxygen gas, and the products will always be carbon dioxide and water. So you'll always know what your product should be. Balancing combustion reactions can be tricky, but I will show you an easy way to do it. So let's get our problem set up. It says our carbon compound is burned with oxygen gas to produce carbon dioxide and water, H2O. These will always be the same for a combustion reaction, so that should make it pretty simple to memorize. When you balance combustion reactions, you're going to do it in a certain order to make it a lot easier. I want you to balance your carbons first, then your hydrogens, then your oxygens last, and you will see why. Go ahead and balance your carbons on both sides and your hydrogens on both sides, and then stop. All right, if we look at our carbons, I have 4 on the left, so we need to make 4 on the right. Hydrogens, I have H10, 10 of them. So I need something here times 2 to make 10 hydrogens. This would be a 5. All right, now when you go to figure out your oxygens, you have to remember that you have oxygens in this compound, but you also have them in this compound. The number on this side on the products has to total the number on that side. So the way that I like to do it is write it underneath. I have 4 times 2. I have 8 oxygens in my carbon dioxide. And I have 5 times 1. I have 5 from my water. All right, I have 13 on this side. How do I split that something times 2 to give me 13? Oh, well that's easy, 6.5. But that's actually kind of odd. We haven't used any half numbers for our coefficients, and you technically cannot leave it that way. What do you think we could do? Well, if you run into that case, you are going to go back through and you're going to double everything. 2, 13, 8, and 10. They're still in the same ratios to each other, but now we have nice even whole numbers as our coefficients. So I always say if you get 0.5, go back and double. Okay, so that's how you would work through a combustion reaction. All right, you will need a calculator for the back of this notes page. So if you don't have one, go ahead and pause it and run and go get it. For this last section, we're going to talk about the mass of atoms and the mass of molecules. Okay, so you can see by my first statement here, to just measure the mass of an atom of hydrogen or oxygen, they're too small. We can't just put an atom on the scale and get its weight. They're just too small to do that. But scientists have taken samples of the elements and they have figured out their masses in atomic mass units. Okay, and that's what these numbers represent underneath the symbol on your periodic table. Okay, so these are our atomic masses. If you have a molecule, like several atoms combined together, in order to figure out the mass of the molecule, you're going to add up the masses of the individual atoms. Okay, so if we want to know the molecular mass of water, we would need to add up the masses of 2 hydrogens and 1 oxygen, and that total would equal the mass of that molecule in atomic mass units. So using your periodic table and a calculator, this is pretty simple to do. If we're going to add up the masses for water, we would say we have 1 hydrogen at a mass of 1.01, and because there's 2 of them, we will multiply by 2, and you'll get 2.02. Oxygen is listed at 16.0, and we're going to add these together to get the mass of our water molecule. Okay, so I get 18.02. In this class, we are going to round to the nearest whole number for our atomic mass units. And you'll see that in calculations, this will make it a lot easier. If you want to use the decimals, that's fine. You can talk to your in-class teachers about what they prefer for grading. But here on the notes page, I'm just going to round to 18 atomic mass units. All right, let's do a harder one together. What if I want to know the molecular mass of sugar? So this would be just like plain old sugar. C6H12O6. Let's list out our elements. You go to your periodic table and get their exact atomic masses. Carbon is 12, and then you look at the subscript and see that there's 6 carbons. Okay, so we get 72. Hydrogen on your periodic table has an atomic mass of 1.01, and there are 12 of those. So you'd get 12.12. And oxygen is 16, and there's 6 of those. So you get 96. Go ahead and add those together and see what you get. You get 180.12, and we'll say that the molecular mass of sugar is 180 atomic mass units. Go ahead and pause this and see if you can do the last one on your own. Remember that this 2 outside the parentheses distributes to the oxygen and it distributes to the phosphorus. Okay, all right, so here's what I got. Calcium, there's 3 of them. Phosphorus, there's 2 of them. Oxygen, there's 8 of them. And my total would come out to be 310.3, or 310 atomic mass units.